this is an image of a standing wave, and this is a standing wave that is a string that is attached to a wall at two ends. So it's attached to one wall there, and it's attached to another wall there. And this is different to a progressive wave because a progressive wave will travel through space. Think about a light wave that goes from the sun to us, that is progressing through that space. But a standing wave is just staying in the same place, it's not going anywhere. So this standing wave here, what we've got is a fixed end and a fixed end, which means that the two ends are not oscillating. Those two ends cannot move up and down, they are fixed in place. If those two ends are fixed in place, then we call them nodes. A node on a standing wave is a point where there is no movement. The points on the wave where there is maximum movement, the maximum amplitude, or maximum displacement, or the amplitude, is the antinodes. I remember that as the nodes as where there's no movement, and antinodes are the amplitude. Now, this is what a standing wave looks like on a piece of string, and this is when you've got two fixed ends, where neither end can move. That's sort of your typical wave shape. Where this can be a bit more difficult is where we come into things like tubes, where you've got a sound wave in a tube, and one of the ends might be open rather than being closed. So I'll draw out what I'm talking about here. So I'm going to imagine a really simple instrument. It's just a tube that looks like that. And this tube is closed at this end and it's open at this end. Now, what that means is because this end is closed, this will be a node. I will get a standing wave in this tube. So to get a standing wave, what I'm imagining is I'm going to maybe just hit this. If you just hit that, it will make a sound. You can test that at home. If you go and get a glass, a tall glass, and you hit it, it will make a sound, probably quite high pitched. And we'll talk about why in a second. As this is a closed end, the air particles cannot be moving here. They are stationary, which means this is a node, very similar to what we had earlier. This is a node. On this diagram, we had nodes at the fixed points at the two ends. We also had nodes here because of how the standing wave is formed. But in our new instrument, where we've got one open end, we still have a node on one of the ends. That gives us this rule that works all the time, is that where you have a closed end, you will have a node. Now, where you have an open end up here, for the standing wave that is formed inside this tube, the open end will have an antinode. This is where the air particles will be moving at their highest amounts, the maximum displacement and amplitude. This is an antinode. That gives us another rule that where we have an open end, we have got an antinode. Where there is an open end, there is an antinode. Now I'm just going to draw my tube a little bit bigger or a little bit wider just to make this next bit a bit clearer for you. What I'm going to do now is I'm going to now draw in what my wave could possibly look like. Now remember, it must be a node down here and it must be an antinode down here. So the first frequency that I could have, which is called the fundamental frequency, the wave would look like this. This is a quarter of a wavelength. This is a quarter of a full wave. If you imagine a full wave like that, the wave that I have inside here is a quarter of it. It's from here to here. It's a quarter of a full wavelength. This is the first possible wave you can have, where one end is a node and another end is an antinode. And then as this oscillates, this end will stay the same. And then the antinode will obviously move up and down. So in the case of this tube, the length of the tube, L, is equal to a quarter of a wavelength. If I think about the next harmonic inside this tube, so I'm going to draw the same tube again, same height. The next harmonic in this tube must also have a node at the bottom and an antinode at the top. So the next possible wave I can have will look like this. That's the first antinode, that's the next node, and then there's an antinode at the top. And then as it oscillates, it will go back between that. So that is my wave, and that is sort of 3/4 of a full wave. So I've drawn this wave here for you for reference. The wave that I get, the standing wave inside the tube, starts there. So that point is that point, and that antinode would be that point there. So you can see this is now 3/4 of the full wavelength of the wave, because I'm still following those same rules I had here. Node here, antinode here. So in this case, the length of the tube now is 3/4 of this new wavelength, or the new wavelength, of the next wavelength up. And so what's happening is you're having to change the frequency of the wave for it to fit in with the new harmonic. And that's how you get different frequencies for different instruments. If you change the length of your tube, or if you change the frequency inside your tube, you'll get a different wave. In another example, what you might have next time is a wave where you've got two open ends. So if you've got an open end and an open end, using the open end rule we had before, an open end must be an antinode. So the first possible wave you can have inside here, where we go from antinode to antinode, where that would be half of a wavelength. So that would be half of a wavelength. Let's imagine that instrument again, and what would the next frequency look like? Well, I have to go from antinode to antinode, and it would look something like that, where this time the length of it is a full wavelength. The next frequency, the next harmonic, I would have 3.5 wavelengths. It would go from antinode to antinode, and it would look something like that. Not the best artist, but you can get the picture, where here the length is 1.5 wavelengths, 3/2 wavelengths.